Okay, and so today's lecture, we are going to talk about non-parametric tests. And so this continues our discussion of various types of single sample and two sample hypothesis tests. And today we'll talk about three specific non-parametric tests, and those include the sign test, the Mann-Whitney U test, and the Wilcoxon sign rank test. And, oh, rats, let's reboot that one. Copied in the wrong overview slide. I'm going to fix this as well as I just saw this one. Apologies. Parametric test. All right, taking two. So today we're going to continue our discussion of hypothesis tests, and we will introduce three non-parametric tests, those being the sign test, the Mann-Whitney U test, and the Wilcoxon sign rank test. As a reminder, your term paper introductions are due at end of day this Friday, February 12th. Ah, bloody. As a reminder, the term paper introduction is due at the end of the day this Friday, February 12th, and then assignment 2 will be due at the end of the day a week from Friday on February 19th. And with that, my dogs have entered the room, just firing on all cylinders this morning. So let's take a deep breath and here we go. Okay, so at the end of today's class, you should be able to conduct a sign test, and there's several different contexts in which we conduct that test, including a single sample test, similar to the one sample Z or T, as well as in the context of a paired test between two samples. The Mann-Whitney U test for independent samples, and then thirdly, the Wilcoxon sign rank test, which is another type of test that can be used for dependent samples. And also as a part of this, you'll hopefully gain an understanding that will allow you to determine when each of these tests are appropriate. With that being said, we won't delve into the normality assessment question because I'm saving that for next week, and you can get a jump start on anything homework related, basically with the three tests that we'll cover today. So, okay. So I guess before we get too far into things, let's just see a quick show of hands or thumbs in terms of how many of you are familiar to any degree with non-parametric tests. Okay, I'm not seeing a lot of hands and thumbs go up at this point, and that's likely what I would expect here. So traditionally, you wouldn't get into this, I would suspect, in most undergraduate engineering statistics courses. We generally stick with the parametric tests. And so just to clarify the terminology, when we talk about parametric tests, we use that term because those tests assume certain underlying distributions for the parameters that we're interested in evaluating. So for example, when we've talked about students and Welch's t-tests, those would be appropriate if our underlying data distributions are normal, and then there are also additional assumptions we introduce in terms of variances being equal or not equal. And even in the case where variances are not equal to one another, if the differences are very extreme, there are even some concerns that would come with respect to the application of Welch's tests. And so non-parametric tests are basically more flexible tests that are robust and useful when some of those underlying assumptions are violated. And so as I had alluded to in the case of a t-test, if our underlying data aren't normally distributed, and keep in mind, this is going to be a particular concern when we're working with smaller samples, more so than larger samples, because with large samples, a lot of the distributions that we're working with will tend to approach normality. And then also we make assumptions about the variances of those samples. And so I don't think I've introduced these words yet this semester necessarily, but when we talk about equal variance, the Impress your friends and family term for that is homoscedastic, and if the variances are unequal, we talk about that variable as being heteroscedastic. And so when these standard assumptions hold, we can use the standard sampling distributions that we've talked about up to this point. So the T, the F, the chi-squared distribution. In order to conduct a statistical test, refer to the reference tables and find the associated p-values ultimately, okay? And so there are a few different cases that would necessitate us using non-parametric tests as an alternative to these more widely used parametric sister tests, as it were. And so the first of those is that the data for the response variable or the dependent variable of interest may not be on an interval scale necessarily. So when we talk about some of the things we've talked about up to this point in class, like speeds and the numbers of crashes or fatalities, these are all cases where those data are measured on an interval scale, and there is a very clear distinction in terms of what those values mean in relation to one another. So for example, a speed of 50 miles per hour is twice as large as a speed of 25 miles per hour. And 10 fatalities is twice as much as 5 fatalities. But oftentimes, and particularly in transportation data, we might run into data that could be ordinal in nature. And so some examples there, I forget whether I've introduced injury severity data, but when someone's involved in a crash, their injury is measured on a 5-point scale, where the least severe is denoted as O, the most severe is defined as K, and the scale goes K, A, B, C, O. And there's not necessarily, we can't say that a fatal injury is 5 times as bad as a crash that results in no injury, for example. So there is a natural ordering in that context, but it's less clear when we're trying to distinguish how much difference there is between the different levels of that variable. And that same type of factor comes into play when we deal with things like survey data, for example. So if someone strongly agrees versus versus neutral on the issue and so forth, there's not necessarily an equal distance, as it were, or magnitude between those respective levels of that scale that we're working with. So that's one case where these non-parametric tests can be useful. Again, the normal distribution is going to be an underlying assumption for many of the tests that will tend to apply in statistics. And so particularly in small samples, departure from normality can give you markedly different results than you would see otherwise. And then thirdly, if the variance is severely unequal between groups, so if you have one group that has a variance that's just much, much larger, and in cases where there's a difference that's significant, Welch's will address that concern to a degree, but as we get further into the course, we'll get into a few examples where there are other issues that arise when we have unequal variances. And so we'll talk a little bit more about that, but those are basically 3 cases. And so when these assumptions are violated, we need to turn to tests that don't have these same stringent assumptions. And so we basically refer to these as non-parametric or also as distribution-free tests, because these can be applied regardless of what the underlying distribution is. So even if those 3 cases, those 3 conditions there are not met, we could still use these non-parametric tests. Now, the consequence of that is basically going to be that they're not as powerful as the parametric alternatives. And so if those assumptions are met, you should go with the parametric test. And so this is basically for those circumstances where that's not the case. Now, with that being said, though, as I noted, you can apply these even if those parametric assumptions are met. Your test will just not be as powerful, which means it will be more difficult for us to reject the null hypothesis when it actually is false. Okay, and so just looking at this graphically, this is just an example here where if we're assuming under the null hypothesis, let's say the median of our distribution is centered at 2, there are a few different ways that can be looked at here. If the actual measured median from our data is centered at 3, it's going to make a big difference when we think about how these hypothesis tests are structured in terms of whether we're rejecting when we should and whether that data is well ascribed by a normal distribution. So in this case, for example, we see one distribution that's normal and one that's very far from normal. And so if we were to apply our traditional parametric procedures on the data that don't follow the normal distribution, as we see right here, we would assume that the probability of obtaining this specific sample here would be equal to 0.1587, when in actuality it would be more than 2 times that amount, so 0.37 here. And so if you think about this, this is a particular concern the further the distribution of your data departs from that underlying normality assumption, okay? And so if this is the case, it's going to be problematic for us to assume that these bottom distributions are well represented by the top distributions, as is the case with our parametric tests. And so as a consequence of that, we're not going to be able to make use of the properties that we know about the normal distribution. We won't be able to refer to the standard normal tables directly here. Although even in the case of the non-parametric tests, we'll talk about how as our samples get larger, we can still make use of the normal distribution for the purposes of evaluating some of these hypothesis tests. And we'll return to that point in a few minutes to add some clarity. Okay. And so the first test that we're going to introduce is one of the simplest and oldest, I guess, non-parametric tests, and that's referred to simply as the sign test. And so this test is frequently used in situations where we have a binomial outcome, so yes, no situations, other types of choice situations. And to that end, it's also often used as an alternative to the paired t-test. So in that instance, you know, we can look at our 2 samples of interest and we can determine whether or not one sample is greater or less than the other. And so that's very similar to that binomial choice situation that we had just alluded to. And so when we're making those comparisons, we're basically, in the case of, say, one sample, we could compare every value in that sample to some reference value of interest, and maybe that's a median value or a mean value, whatever the case may be. And we can count the number of cases where our sample value is larger than that reference value or less than that reference value. Or in the case of paired data, we can look at the number of times that specific observations in the first sample are greater than its paired observation in the second sample, and vice versa for negative differences as well. And so if we think about it from that perspective, like from a 2-sample scenario case, if we're doing a paired test, if we consistently see that the paired values in one sample are greater than or less than the other, that's likely a good indication that there's some effect at play here, and there's evidence that would be able to potentially refute our null hypothesis that those distributions would be the same ultimately. Okay. And so as I had alluded to previously, you know, this test is often used when our response is either difficult to quantify or can only be measured qualitatively. So things got better or worse, or there was no change, but there's not necessarily, we can't quantify the magnitude of those differences. We just know that things got better or worse, but we can't ascribe a specific value to that, for example, like when we think about the survey data example. And so under this setting, if our null hypothesis is true, and so if those distributions are the same, we have the same number of differences that are positive and negative between the 2 samples, then the number of plus signs or minus signs, it's arbitrary which way we structure this test, is known to follow a binomial distribution. And let's just get a quick show of hands and thumbs again. How many of you have some recollection of the binomial distribution? Okay, so we've got a little bit of familiarity out there in the audience. And so in this specific case, the binomial distribution, anytime we have a dichotomous outcome, so it can take either a yes or no, classified into one of two categories. Our null hypothesis in this setting is basically that there's no difference between those. And so the probability of observing a plus or the probability of observing a minus would basically be equal to 0.5 for each individual observation if we're assuming we're observing a number of different observations in our sample. And so our alternative hypotheses then, depending if we're conducting a two-sided or one-sided test, would be that that probability is not equal to 0.5, is greater than 0.5, or is less than 0.5, depending upon which direction we would presume that alternative hypothesis may lie based on the sample data we're working with, okay? And so just to refresh everyone's memory, the binomial distribution has parameters n and p, and it basically is a probability distribution that characterizes the number of successes, which will denote x, that would be experienced over a series of n independent experiments, or in our case, if we observe n individuals or n vehicles or n units of some type. And then in that instance, we can define a success. It's arbitrary whether or not success has a good or bad connotation here, but that would represent that observation falling into some specific group of interest. It could be a yes or a no on a survey response. It could be any of the two groups that we're comparing. And in that setting, as I had noted, we're defining the probability of x basically being equal to 1 in any of these experiments as p, and in the converse, the probability of a failure would be denoted as q, or 1 minus p. And so let's say we've got a sample of data xi from x of 1 to x of n. And then we know that the probability density function for that, if we assume the binomial distribution, is as given by this formula here. So this should hopefully look familiar to everyone. So specifically in the sign test, we would set this up so that this probability is equal to 0.5. Our sample size, I'm going to introduce an example problem on the next series of slides where we'll work with a sample of 10, for example. But in that case, for example, if we had 10 trials, we could determine the probability of having X successes. And apologies, let me do one quick fix here. So we could determine the probability of having X successes among those N trials with the probability of 0.5. And so, for example, from that, we could then look at what the cumulative probabilities would look like coming from that binomial distribution. And if we're on either the very high end, so if X were equal to 9 or 10, or on the very low end with X being equal to 0 or 1, obviously in those cases, it would be very unlikely we would have 0, 1, 9, or 10 successes among 10 trials if our probability of success for any individual trial was 0.5, right? And so when we look at the binomial distribution, this is just showing us for relatively small samples ranging from 2 to 6. This is telling us how likely it is for different values of P that we would observe a certain number of successes, okay? And so the column that we're particularly interested in here is the column with a baseline probability of 0.5. And so in the simplest case here, if we just took a sample of 2, in this case, there's a 25% probability that you would observe 0 in that case, a 25% probability you would observe 1, and that actually is a typo right in this, unless I'm, oh, sorry, I missed that up. So if we look at the 0.5 column here, This is just telling us the cumulative probabilities within each of those respective ranges here, okay? And so we could determine with any of these, if we had a sample size of 5, what's our likelihood of having 0 successes among those 5 trials? It would be 3% in this case, okay? Our likelihood of having successes in 4 of the trials, up to, in this case, it would be 0.9688. So that would be the same 3.13% here. So these are cumulative probabilities in this table. I'll be presenting a few different formulations of this binomial distribution table. So apologies for the mix up there. And so with the case we're working with, we're concerned just with that 0.5 distribution. And so let's say, hypothetically, drivers are asked whether they're interested in purchasing or leasing an autonomous vehicle, and we wish to determine whether or not there's a general consensus as to people having a preference for or against the purchasing of an AV or leasing it under whatever context we're evaluating this. And so in this case, our underlying hypothesis is again going to be that that probability is equal to 0.5. So basically it's going to be split. If that null hypothesis that there's no preference is true, we'd expect to see the same number of yeses and nos to that survey response question as an example, okay? And we could look at a two-sided alternative where that preference could be in either direction, or we could look at the one-sided alternatives there. And so if that probability was greater than 0.5, that would, based on the way we're defining this, indicate a preference towards purchasing or leasing an AV. And if it's less than 0.5, we'd be going in the other direction, and those people would tend to be less inclined to acquire an AV, okay? And so in this setting, we're basically comparing the preference of each individual to that baseline probability of 0.5. So if they answer yes to that survey response, that person's probability is 1. We've observed that. If that person's preference, the response to that question is no, their probability is 0. And so we can compare each of those individual observations to that baseline probability of 0.5. And so to that end, any person who is in favor of acquiring an AV would be assigned a plus sign. Anyone who would be against that was assigned a minus sign, and hence the name in this case, the sign test. And so in the case of small samples, we can go directly to that binomial distribution table in order to make the determination as to whether or not we can reject that null hypothesis, okay? So to start nice and simple, let's assume that 6 individuals are surveyed and 5 of these individuals have indicated they're in favor of purchasing or leasing an AV. We can then basically go directly to that binomial distribution table as shown here on the following slide. So we've got a sample of 6 observations here. We have the cumulative probabilities of observing 0 up to 6 successes here respectively. And so if we look at our probability of having 5 successes, we'll notice that that's going to be 0.9844. And so as a consequence of that, we know our probability of being at that extreme of a value is going to be 0.0156. And so that's the value then that we would explicitly compare to whatever our significance level is for that test. So we're basically comparing our observed probability to alpha. If it's less than 0.05, that tells us that our probability of observing that extreme of an outcome is going to be very unlikely just based on random chance. And so consequently, we can reject the null hypothesis and claim that there is in fact a preference towards purchasing or leasing an autonomous vehicle, okay? And we can continue on that same example here. In this case, we're going to revisit the collision data that was represented in some of our 2-sample tests, the parametric tests we had talked about previously. And so as you may recall, in this context, we had a series of 10 intersections. Those intersections had experienced a preponderance of rear-end crashes, and so we changed the signal timings in order to try to address that. And so consequently, we had evaluated these data using both students and Welch's t-test as well as a paired t-test. And you may recall in this context, the paired t-test worked particularly well because we did see that some of these locations, like 3 and 6, for example, tended to experience more crashes during both of the periods, whereas other locations like 9 and 10 tended to be on the lower end during both of those time periods. And so there was clear correlation between these respective outcomes. And so just as we had done with the paired t-test in the case of the sign test, we were basically looking at those differences, and I'm just putting a plus sign here wherever we see a higher number of crashes before the signal timing change. And in the case, if crashes had gone up in any of those cases, I would have indicated a minus sign here. Interestingly, at 2 of these locations, there weren't any changes whatsoever. And so the way that we handle that scenario, anytime there's a tie, we basically exclude those ties from the underlying data set. And there isn't a strong consensus in the research literature, but one concern that would arise here is if you have a very large number of ties, so a lot of cases where there aren't any differences observed whatsoever, then this test can become somewhat tenuous. But in most instances where we're applying this, that's not a concern. Now, we can get a little bit further into the weeds on that topic, but for our intents and purposes, in most cases, the data are structured such that we generally wouldn't have an issue with just discarding those. And so the implication here is that would reduce our sample size then from 10 to 8. So we are essentially sacrificing some degrees of freedom essentially in how we would conduct this test. But hopefully everybody's with me here on the setup. And so in this case, we're again going to our binomial distribution table here. And so with n equal 8 and a probability of 0.5, this case is obviously a very clear case because at all 8 of those locations, crashes went down, and the probability of that occurring is practically 0.004. And so as a consequence of this, we can then reject the null hypothesis and claim that the signal timing changes were in fact effective in that case. Okay. All right, perfect. Now, interestingly, if our sample sizes are sufficiently large, and the number you'll see cited frequently in the literature is anything greater than 20, the number of positive or negative differences or signs can be approximated by a normal distribution with mean and standard deviation as shown here. And this should hopefully be obvious. So if we have a sample of any size and the null hypothesis is true, we would expect that half of those observations would be plus and half would be minus, is where we arrive at this estimate of the mean from. And then the standard deviation of that quantity is just going to be the square root of 0.25 times n. And again, this is basically, if you recall back to statistics, and you probably talked about how the binomial distribution can be approximated by the normal distribution at large samples, and this is what the mean and standard deviation of those quantities would be in that context. And so if that's the mean and standard deviation of our number of successes or failures, we can use those in a standard normal test and simply take our number of successes minus the expected number of successes we would expect to see if the null were true, divided by that corresponding standard deviation. And so this test statistic would then tend to follow the standard normal distribution. Okay, so even though we've determined our underlying distribution is not normal, if our sample size is large enough, the distribution of the mean and the standard deviation would tend to follow the standard normal distribution here as well. So we'll follow up with one quick example here as well. So we'll continue on the preceding example, but it's difficult for me to fit data for 50 intersections in a clear to read table or slides. I'm just providing the description here in words. So let's assume we had introduced signal timing changes at 50 intersections, and among these 50, Crashes were found to go up at 15 locations, down at 25 locations. So we don't see as consistent of improvements as we had in that 10 intersection sample. And crashes were unchanged at 10 locations. Okay, so we're going to take this and we're going to apply the sign test that we had just talked through. And so first of all, we needed to figure out how many pluses we would expect to see. Now, before we do that, the first thing we need to figure out here is what is n in this case, and just be careful here because n is not 50. So what would n be within this context that we're talking about? Anybody on this one?
Should be 40.
Right, exactly. Should be 40 because we got the 10 ties. We're dismissing those 10 ties from our data set, and consequently 0.5 times 40, we'd expect to see 20 successes. So crashes would have gone down or up, depending how we define a success. I guess in this case, I would prefer crashes going down. We would expect to see 20 successes. And so we saw at 25 rather than 20. And so that gives us just a general sense of the magnitude of the test here. And so that difference, obviously qualitatively, isn't as large as we saw in the 10 observation sample. The standard deviation of that quantity, again, using 40 for n, is 3.16. And then when we apply the standard normal test, we are just going to take our 25 successes minus our expected number, which is 20, divided by 3.16. And our calculated test statistic is 1.58. If we were conducting this as a one-sided test, what would our corresponding critical value at alpha of 0.05 be equal to? Does anybody recall? So standard normal, the top 5% of that distribution would be any number greater than or equal to, yeah, thank you, Jordan, 1.64 or 1.645 if we want to be really obsessive compulsive about that. Generally speaking, that 0.005 doesn't make a big difference. And so in this case, we're slightly below that number, so we do not have sufficient evidence to reject the null hypothesis in this case, okay? And so essentially, there's not a big difference between what we had done previously with the binomial distribution table and what we're applying here. We're just trying to assess how likely it is we would observe the number of successes or failures that we did based on the sample data under the assumption that there is no difference, which is what our null is stating in all of these cases, okay? And so as the samples get larger, you know, we don't need to go through a binomial distribution table with n equal to 50 or 100 or whatever the case may be. In those instances, we can just make use of the fact that that statistical distribution is converging towards the normal distribution as our sample size is increased, okay? All right, now that is appropriate for either paired dependent sample tests or for one sample test. However, it would be nice if we had an analogous alternative to Student's or Welch's t-test. And so to that end, we use what's referred to as the Mann-Whitney U-test as a non-parametric alternative to the independent sample t-test, okay? So this test would be appropriate to use when those underlying populations are not normally distributed, so they could follow a Poisson distribution or an exponential distribution or something that's very divergent from normal, or when sample sizes are so small that it's not really practical for us to try to assess normality. So again, we're using that arbitrary cut point somewhat of 20. And likewise, if our response variable is ordinal in nature rather than interval in nature, so back to the point where we have somewhat unequal distances between the different levels of our dependent variable, okay? And so thinking about that conceptually, we're basically, and the same is true of the sign test, what we're basically assessing is whether or not one of those distributions is shifted to the right or left of the other distribution. Okay, and so because what we're basically doing is we're just comparing the relative values between these samples. So similar in some contexts what we're doing with the sign test previous to this. And so in order to conduct this test, what we basically do, we take both of our samples and we combine the data. We want to make sure we retain the labels so we know which sample each of those observations came from. And then we simply rank all those observations in ascending order. So from the smallest to the largest, we label each of those observations based upon what its rank is within that sample. And so the smallest observation is given a rank of 1, the largest observation is given a rank of n. And then what we do is just simply sum the ranks across those two samples. And so the sum of the ranks for sample 1 is denoted R1. The sum of the ranks from sample 2 is denoted as R2. And with that information in hand, then we can make use of the U statistic, which is defined as we see right here, okay? So U is going to be equal to the product of those sample sizes plus N1 times N1 plus 1 over 2 minus R1, where again, R1 is the summed rank for sample 1. And what we'll basically find, the same type of rule of thumb we've introduced previously for relatively large samples, so total sample size of 20, so we'll typically say 10 in each is a target. We'll find that U is approximately normally distributed. Its mean is going to be equal to N1 times N2 over 2. And its variance, or sorry, its standard deviation. You can tell I've made some changes to my non-parametric slides here. Apologies, I'll reboot that one. And so again, we'll make use of the fact here that for relatively large samples, which we'll say a total of 20 or 10 observations in each sample, U is approximately normally distributed with a mean of N1 times N2 over 2 and a standard deviation that's equal to the square root of N1, N2 product times N1 plus N2 plus 1 over 12, okay? And so as we saw in the sign case, as the sample size increases, this test statistic U also tends towards a standard normal distribution. And so the corresponding large sample test statistic, as you can probably guess here, Z is going to just be equal to U, which we obtain from this equation, minus our expected value or mean value of U if the null were true, divided by the corresponding standard deviation. Okay. And now we'll return to our same example that we've been working with previously, where we have our crashes before and after the signal timing adjustments, and we'll use the same data set to demonstrate the application of the Mann-Whitney U example, okay? So as a reminder, what we're going to do here is basically combine both of these samples into a single ranked data set, maintain details of which of the two samples these data were drawn from. And then from there, we'll calculate the corresponding test statistics. Okay, so the ranked data are demonstrated on the right here. And so all I've done is taken those 20 observations from the preceding table and rank them in ascending order. And so the fewest number of crashes that was experienced at any given site in a particular year was 4, up to a maximum of 14. And we've ranked those accordingly. You see the sample that each value is drawn from is indicated on the left. And you'll notice here, we do have a significant number of ties. And so anytime we run into a tie, we basically average what those ranks would be. So for example, we only have the one observation at 4, so that's straightforward, but we have 2 5s. And so those are the second and third observations. So if we take 2 plus 3, that gives us 2.5. So that's where this number is coming from. Likewise, this is an average of 4 and 5, 6 and 7. Down here, these are ranks 8 through 11. And so if we average those 4, that's where the 9.5 comes from. And so forth and so on until we get to our last 3 observations, which is where we are clear of any ties. And so those would be the 18th, 19th, and 20th ranked observations, okay? And so what we're going to do now is basically sum those ranks within the respective sample. And so in R1, that sum is equal to 125. In R2, if we sum those respective ranks, those average ranks are equal to 85. And so this is reflective basically of the magnitudes of those values within the two samples. So we tended to see significantly more crashes in the first sample, and so we see significantly larger rank values here because those location one, or sample one, sorry, is tending to come much further down the list. You see a lot of clusters of ones, whereas a lot of the twos are clustered towards the top, which is why we see the lower value here for R2, okay? And so we'll then use these values as inputs to the U statistic. And so it's arbitrary basically which way we set this up, but by convention, we basically take the rank of the first sample here and calculate that U statistic accordingly. And so our expected value of U, or the mean that we're comparing against, would be a mean rank of 50. And so basically here we have 20 values. If we take the average rank of those 20 values across the two samples, we would expect to see 50 as the value of that U across both of the samples, if the null were true in any case. And the standard deviation can be calculated using those same sample sizes. We find that that's equal to 13.23. And so at this point, we can plug that mean and standard deviation into our large sample test statistic. And so Z in this case, we take our calculated value of 125 from the preceding slide. We subtract off the mean of 50 and divide by 13.23. And that test statistic in this case gives us 5.67, which is significantly above the critical value for a one-sided or two-sided test in this case. And so we can again reject the null and conclude that our signal timing changes have in fact had an impact. And so you'll notice this gives us a much larger test statistic than when we used the simpler sign test previously. And so that's accounting for the fact that we're now making use of the magnitude of these differences between the respective observations as well. And so consequently, this test is quite a bit more powerful as compared to the sign test, okay? All right, and then the final test we're going to talk about today is the Wilcoxon signed rank test. And this is basically a second alternative to the paired t-test. Previously, we had used the sign test for these same purposes. Now, the big difference that comes into play here is with the sign test, we really lose a lot of information about our sample and the samples and the differences between those samples. So let's say in the case we're working with here where crashes went down, if crashes went down by 1 versus 50, we would assign the exact same sign to that and we'd get the same amount of information from that 50 crash decrease as that 1 crash decrease. And so obviously we'd want to give greater weight where greater differences are observed. And so that's what we're basically doing in the signed rank test, is that the magnitude of those paired differences is now taken into account. And so we're basically ranking the paired differences rather than just taking the differences in the signs, for example, as we had in the preceding case. And so in this case, this is a test we'll apply frequently again when our data are either non-normal, when our sample size is small, or when the response is ordinal in nature, similar to the other cases for the non-parametric tests we had introduced previously. And so just like we had done in the paired t-test, the first thing we're going to do is take the differences between the paired observations. So we can take the number of crashes before minus the number of crashes that occurred afterwards. In this case, we are again going to have to exclude any differences which are 0 because we simply don't have a mechanism by which we can include those in our calculated test statistic. And then the absolute values of these differences are ranked from smallest to largest, regardless of what the sign may be, just as we had done in the preceding tests. And if any of the differences between those are equal, we basically average those ranks, okay? And then the t-statistic is basically going to be the smaller of the sums of those pluses or minuses. So we sum up the ranks of the positive differences, the ranks of the negative differences, and then we take whichever of those two is smaller, and that is going to be our t-statistic. I cringe at the fact that this is also a t-statistic because it's obviously not the same t-statistic we've talked about up to this point. It just happens to be the way that this was defined by Wilcoxon in the development of this test. And so as the sample size increases, as we've seen in the other cases, t is approximated by a normal distribution. So as we saw in the other t-tests we've talked about, that t approaches normality at larger sample sizes. Although again, I must restate, this is a different t. And so this convergence is recommended to be good for samples of larger than 25. So slightly beyond that 20, but we're in the same range typically for most of these tests. And a lot of this is somewhat arbitrary in nature. We'd want minimum sample sizes of between 20 and 30 to make use of some of those large sample properties for the normal approximation. Okay. And so for this test statistic, the mean of that t distribution that we demonstrated how to calculate previously is going to be n times n plus 1 over 4. The standard deviation of t is going to be given by this formula here. So the sample size, and again here, since we're dealing with paired samples, n is the number of pairs, not the number of unique numbers that we've observed. So if we had 10 locations, it would be 10 rather than the 20 data points we're observing. And so the square root of n times n plus 1 times 2n plus 1 over 24. And as you can probably guess where we're going here, that's going to then be distributed as a z-statistic, where we take t minus that mean expected value of t if the null were true, divided by sigma t. Okay? And so in this case, we're going to return yet again to our intersection data here. I have made a note here up at the top. So this is a relatively small sample here. And so though we're going to use that normal approximation, I should note that we would prefer to have larger samples in order to apply this test in practice. But again, just to allow for an apples to apples comparison with some of the preceding tests. And so we've gone through, you see each of those respective differences here. And again, we're ranking those basically in ascending order. We have ties for locations 9 and 10, which experience the same number of crashes between the before and after period. And then the smallest decrease in crashes was 1 crash, which was experienced at locations 2, 4, and 6. And so the average rank for the first, second, and third smallest differences in this case would be 2. And similarly, we had some ties between observations 4 and 5 and 6 and 7. And then location 8 saw the largest decline in crashes of 5. And so that's the highest rank then in this case. And so we'll take those ranks and we'll translate that to calculate our t statistics here. And so our expected value of t would be 18 in the event the null were true. The standard deviation of that quantity would be 7.14. And in this case, interestingly, again, we had all positive differences here, no negative differences. And so that sum is 36, which is significantly larger than that expected value. And so in this case, our calculated z statistic is then 2.52. And this again is going to be significantly larger than that critical value of 1.645 or 1.65 that we've been working with historically through these examples. Okay, so the conclusion then, as in the other cases, is that we can reject the null and we find that the signal timings have in fact made a difference here. Okay. And so ultimately, when we look at all of these different tests that have been applied, it's somewhat interesting, and what we'll look to do in the next homework assignment is to basically compare the results of these non-parametric tests to the parametric alternatives that we had worked through on the last assignment. And that'll help to give us a sense as to the magnitude of differences we would expect to see. Ultimately, the parametric and non-parametric tests will tend to lead us towards similar conclusions, but the big concern here is that you have a parametric test and those assumptions are not met. You could basically have insufficient evidence to reject the null, but you don't realize that, given the fact that you're relying on parametric distributions whose properties aren't necessarily well met. And then, as I had alluded to previously, in contrast, if we use the non-parametric tests, those are going to be better, more robust and powerful tests when those violations of the underlying assumptions do occur. However, if those assumptions are met, it's going to be less powerful. And so it really varies quite a bit depending upon the particulars of your data set, how large those differences are between the tests. But as you saw in this case, many of these, the T tests and the non-parametric alternatives were fairly similar to one another in direction. The magnitude of some of those tests was larger in some instances for the parametric tests, but that's something we'll look in at greater detail with a much larger sample on the homework assignment. So with that, that wraps up basically all the tests we would use to compare the average or median or central values across two samples. We'll begin talking in the near term about analysis of variance, where we can extend this to 3 or more samples. But before we get to that point, there are a few additional types of tests that we'll start to talk about next week, and that would include tests of proportions, for example, and we'll introduce some tests for determining whether or not that normality assumption is met as well. And it looks like I have the correct deadlines here for the term paper introduction of this Friday and assignment 2 for next Friday.